Scientists put a tiny metal object in two places at once. Quantum physics just got stranger. Imagine holding a tiny fragment of metal in your hand. According to everyday physics, that object must occupy one definite position at any given moment. It cannot be in two places simultaneously. Yet a remarkable new experiment has pushed quantum mechanics into territory that sounds almost impossible. Scientists have demonstrated that microscopic metallic particles made of thousands of atoms can behave as though they exist in multiple places at once. The breakthrough, achieved by researchers at the University of Vienna and University of Duisburg-Essen, represents one of the strongest demonstrations yet that the bizarre laws of quantum mechanics continue to operate far beyond the scale, where most people would expect them to break down. Quantum physics has always challenged human intuition. At microscopic scales, particles do not behave like tiny billiard balls, moving along precise paths. Instead, they behave as waves of probability, spreading through space and interfering with themselves. This strange principle, known as wave-particle duality, has been repeatedly confirmed for electrons, atoms, and small molecules. In famous double-slit experiments, single particles can travel through multiple paths simultaneously and generate interference patterns as though each particle interacts with itself like a wave. But as systems become larger and more complex, the surrounding environment usually destroys these delicate quantum effects. Everyday objects appear classical because their quantum behavior rapidly disappears through interactions with the outside world. The new experiment dramatically extends the boundary where quantum mechanics has been directly tested. Instead of working with tiny atoms or simple molecules, the researchers used metallic nanoparticles composed of between 5,000 and 10,000 sodium atoms. These clusters measured roughly 8 nanometers across, comparable in size to advanced semiconductor components found in modern electronics. Each particle possessed a mass greater than 170,000 atomic mass units, making them vastly heavier than the kinds of particles normally used in interference experiments. Intuitively, most people would expect such a metallic object to behave like an ordinary classical particle, with a well-defined position. Instead, the experiment revealed unmistakable quantum interference, proving that even these surprisingly large lumps of matter still obey quantum rules. To perform the experiment, the scientists first generated ultracold sodium clusters and carefully directed them through an elaborate interferometer system. The core of the setup relied on 3 diffraction gratings created entirely by ultraviolet laser beams. The first laser effectively localized each particle with extraordinary precision while simultaneously placing it into a quantum superposition state. In quantum mechanics, superposition means that the particle does not follow one single trajectory. Instead, its quantum state spreads across multiple possible paths at the same time. As these overlapping paths later recombined inside the apparatus, they produced a striped interference pattern, the unmistakable signature of wave-like quantum behavior. What makes the results so extraordinary is the scale involved. During their flight through the interferometer, the sodium clusters did not remain confined to a single tiny location. Their quantum states extended over regions many times larger than the particles themselves. In effect, each metallic nanoparticle behaved as though it existed simultaneously in multiple different positions. Physicists often describe such states using the language of Schrödinger's famous thought experiment, where a cat exists in a superposition of alive and dead states until observed. Here, instead of a cat, scientists created what could be described as a Schrödinger metal lump, a microscopic piece of metal that was both here and not here at the same time. The Aki achievement also sets a new benchmark for testing the foundations of quantum theory itself. Physicists have long wondered whether quantum mechanics remains universally valid at larger and larger scales, or whether some unknown mechanism eventually forces objects to behave classically. To compare experiments designed to probe these limits, researchers developed a concept known as macroscopicity, which measures how strongly a given experiment tests possible deviations from standard quantum mechanics. The Vienna team achieved a macroscopicity value significantly beyond previous records, pushing experimental tests of quantum superposition into a new regime. The researchers noted that reaching an equivalent benchmark using electron superpositions alone would require maintaining coherent quantum states for periods approaching 100 million years. In contrast, the metallic nanoparticles achieved comparable sensitivity within only fractions of a second. Beyond its philosophical implications, the experiment also opens important technological possibilities. The interferometer developed for the study functions as an extraordinarily sensitive force detector, capable of measuring forces of almost unimaginable weakness. Such sensitivity could eventually enable new forms of nanoscale sensing, precision measurements of electromagnetic interactions, and advanced studies of isolated quantum materials. Future versions of the system may become even more precise, potentially contributing to developments in nanotechnology, quantum metrology, and ultra-sensitive detection systems. Perhaps most importantly, this work pushes science closer to answering one of the deepest questions in physics: where does the boundary between the quantum world and the classical world actually lie? Everyday experience suggests that large objects cannot exist in multiple places at once. Yet experiments like this continue to expand the range where quantum mechanics remains valid. If particles made of thousands of atoms can still behave as coherent quantum waves, then the dividing line between ordinary reality and quantum weirdness may be far less fundamental than once believed. The researchers now plan to extend these experiments to even larger particles and more complex materials, potentially pushing quantum superposition several orders of magnitude further. Each step forces scientists to confront an increasingly unsettling possibility. The strange quantum rules governing atoms and subatomic particles may not merely describe the microscopic world. They may be the true underlying rules of reality itself, hidden beneath the stable classical world we experience every day.